Welcome to the UGC lecture series. This is the PG Pathashala lecture series on computer science, and we are talking about the paper data structures. In this particular module, we will be talking about topological sorting, but now as an application of DFS or depth first search. As you remember, in the previous module also we have discussed in detail what the concept of topological sorting, and we have explained topological sorting algorithm. But in this particular module, we are also going to talk again about topological sorting, but as an application of a depth first search traversal of a graph. Here is the people responsible for the development of this particular module. Let us look at the learning objectives of this module. The learning objectives of this module are to understand the concept of topological ordering, but now as an application of DFS or depth first search, and discuss the complexity of topological sorting. And then we are also going to discuss to a limited extent the proof of correctness of this particular algorithm. And the terms here are obviously topological sorting and depth first search. Now, let us first look at depth first search. We have seen depth first search, but we have seen depth first search more, or DFS as it is popularly called, more as a tree traversal system. Here we are looking at depth first search as a graph traversal. So, in directed graphs we traverse edges only along the direction of the edges. In the directed DFS algorithm we can distinguish 4 types of edges. This is very interesting aspect that we are going to talk about. We are dividing the edges into 4. So, discovery edges, back edges, forward edges and cross edges. We will go into these in detail as we go along. So, a directed depth first search starting at a vertex S determines the vertices reachable from that particular start. Okay. So, if we explore from A and if we have marked BCD as well as anything connected and added all of them into a topological sort in backward order. Now, here in DFS we will go in backward order, that is very interesting way. If you finish BCD we can add A. So, that is the idea. So, basically all you have to do is to run an DFS, but add the fact that at the end of the recursive function you will add the node the DFS was called from to the end of the topological sort. So, you run a DFS and at the end of the recursive function where you have called the DFS, the node that called the DFS is added at the end of the topological sort. Okay. So, for example, if you had called from A BCD, then after you finish BCD you add A. Now, let us have a small discussion on depth first search and DAGs. Now, argue that a directed graph G is acyclic if and only if a DFF of G yields no back edges. Now, forward if G is acyclic there will be no back edges. A back edge implies a cycle. A back edge is from any node back to itself. So, if no back edges G is acyclic. The contrapositive argument is if G has a cycle then there will exist a back edge. Let V be a vertex on the cycle first discovered and U be a predecessor of V in the cycle. When V is discovered, whole cycle is white, or that is it is discovered. You must visit everything reachable from V before returning from the DFS visit, because DFS visit says that everything reachable from a vertex has to be visited. So, path from U to V is yellow. Yellow means some of these use coloring examples to say yellow means that is a back edge. Now, let us take the case of getting dressed again. This is what we have already seen in the last example, just to give you an idea. So, the topological ordering has to be the same. So, the topological ordering here it could be shoes before you put shoes you should have finished socks, underwear and pants. So, the idea is that shoes should come after the socks and all that. Watch can come anywhere and so on. Okay. Now, the algorithm for topological sorting using the depth first search is call the depth first search of the graph to compute finishing times f of v for each vertex v. We will talk about this finishing time also again of any vertex. As each vertex is finished, insert it into the front of a linked list and then return the linked list of vertices. Note the result is just a list of vertices in order of decreasing finishing times. So, decreasing finishing time. Okay. So, Now, let us look at what is this edge classification. Previously, we discussed what is a back edge, forward edge. I mean, we did not discuss, we just listed it. Now, we will discuss. So, an edge UV of a graph is classified as a tree edge if and only if U discovers U during the DFS. It is reachable from, if you go from U, you can reach V. So, the P of V is equal to U, that is you have reached V from U. Then if UV is not a tree edge, then it is a forward edge. So, it is not a tree edge, forward edge if and only if U is an ancestor of V in the DFS tree. Here when we say tree edge, it means DFS. Please note, when we talk about graph and the DFS tree, they are two different things. So, graph is different, a DFS is the order in which you traverse the graph. So, and you can traverse a graph in using any edges, only those edges form the DFS tree. So, forward edge is if and only if U is an ancestor of V in the DFS tree, and a back edge is if and only if U is a descendant of V in the DFS tree, opposite of each other. Then you have also a cross edge. A cross edge is an U which is neither an ancestor or a descendant of V. We will understand this further as we take an example. So, basically we have three edges: forward edge, back edge and cross edge. So, forward edge is U is an ancestor, backward edge is U is a descendant, and cross edge if U is neither an ancestor nor a descendant of the node V. Okay. Now, let us explain those concepts a little more in detail. Now, suppose you have this particular ABC, this ABC are tree edges, that is a depth first search, remember, okay. And C to B is a back edge and C to A is also a back edge, okay. Then A to C is a forward edge because A is an ancestor, remember the definition of, one minute, ABC is a depth first search, okay. Now, remember the definition of back edge. So, C is a back edge if B to C. So, C is a CB is a back edge if that it is a U and V. So, it is a descendant, okay. So, not ancestor, and remember the forward edge A and C, AC is a forward edge if A is the predecessor of C or ancestor of C. Now, you have again this. Now, if you look here, C is neither an ancestor nor a descendant of B. So, it is called a cross edge. You also have CD, CC, here we have just put it as CC, also a cross edge. So, the edge classification depends on the particular DFS tree. If you have another DFS tree, then the definition is different. So, you have understood tree edge is how you traverse the graph using the DFS. Forward edge is if AB or UV, U is an ancestor of V, backward edge if V is an ancestor of U, and cross edge is when the node the vertices are neither as descendants or ancestors of the node. Now, it depends on the particular tree. So, suppose you have A, B, C and you have A and C. Look at this, they are two different depth first searches. Now, here A and C is a forward edge, while in the second one B C is a cross edge because B is neither a descendant or ancestor of C. So, if that is a DFS, then this is a back edge. So, this is the idea. So, both are valid. Now, can there be back edges in a DFS on a DAG? No, back edges actually mean a cycle. So, a graph G is a DAG when there is no back edge, we have discussed this earlier, classified by the DFS. Okay. Now, topological sort algorithm, we can use a DFS in algorithm to determine a topological sort. The idea is when you do a DFS on a directed acyclic graph DAG, the number eventually you will reach a node with no outgoing edges, because direct acyclic graph you have to do a depth first search, you will reach, because if this never happen you hit a cycle because the number of nodes is finite. Okay. This node that you reach in a DFS is safe to place at the end of the topological sort. That is, for example, we had the example of leaving for work. So, that will be the last one you do. Now, what we find is if we have added each of the vertices below a vertex into our topological sort, it is safe then to add this one in. So, if you have finished all the from wherever you call you finished everything else, you can add this. If you added in leaving for work at the end, then we are surely add taking a SHA. So, this is how we do this. So, run a DFS, when a vertex is finished, output it, vertex is output in reverse topological order. So, this is what we will talk about correctness a little bit. The time is the order of V plus E. So, DFA start a DFS, do a DFS starting from some node. The last node you reach before you are forced to backtrack, that is the end of the topological sort. Continuing with your DFS, placing each dead node into the topological sort in a backward order. So, call DFS to compute finishing times for each vertex V. As each vertex is finished, insert it into the front of a linked list and return the linked list of vertices. So, that is the basic algorithm. Now, we will discuss something called a timestamp of a vertex also. Each vertex V has two timestamps, D of V, that is the time when the node V or the vertex V is first discovered, and F of V records when the search finishes examining its adjacencies, that is all its neighbors or all the nodes that come to it have been examined. For every vertex U, the finishing the F of the D of U, that is the first discovered and the finishing the search, the first discovered time will be less than the finishing. Now, let us take an example. This is taken from this particular tutorial. So, you have a graph like this. So, you want to compute call DFS of G to compute the finishing times of the vertices. So, let us say we start with at some vertex. So, let us assume initially the remember D, the discovery time and finishing time, everything is put as infinity to start with. Okay, for all nodes. Now, let us say at that point of time the time is equal to 1. Now, let us say we start the DFS from the vertex C. So, the time becomes 2. Before that okay, we start now we will color this as gray and black. If you have not yet done anything, it is white. If you have discovered it, it is white gray, and if you have finished it, it is black. That is the assumption they make. So, let us say we start from C. So, we have discovered C. So, the discovery time is 1 because the time is at now is 1 and it becomes gray. Okay. Now, once we have discovered it, the time changes to 2. Now, from C you can go either to D or E. Let us assume that we go to D. Okay. So, after C is finished, you can go to D. Okay. So, what we do is let us assume we discover the vertex D. Now, when we discover the vertex D, okay, it becomes 2, okay, and that is we have discovered it, and after we discover it, the time becomes 3 because it was at 2 before. Okay. After you finish D, we discover we could have gone the only way you can go is to F. So, we discover node F, it becomes gray and its time becomes 3. Now, this 3 is what is up there. Okay. Now, after we reach F, the time becomes 4 and F is done, move back to D because from F you cannot go anywhere. So, you go back to D. So, now F becomes finished and F is put at, because you have remember here it is not where you can go and whether it is reached or not. The way we do this topological sort using this depth first search tree is if you have finished the node, then you move back to D. So, when you move back to D, so move back to D, time becomes F. Now, D is done, okay, and we have to move back to C. So, you move back to C. Once you move back to C, the time is changing accordingly. When you move back to C, now you can go to E, the only place you can go to Z. So, we discover thing at that time the point is 6. Remember, look at the time when we finish its child is over. So, D is over. Next we discover E and its discovery time is 6. Now, both edges from E are cross edges because from E to F, F is both edges from E are cross edges because they are not tree nodes. So, they are cross edges. So, what happens? They are cross edges, you number it accordingly and E is gets over. So, that time is 7. Remember, you have to check all this. Once E is over, what we do? Now, you have to do other nodes, but from C you can't go anywhere. So, you start with A. So, let us go to A. So, the discovery time is 8 and now C is also done. Okay. E is done. So, move back to C, C is done. If there is CF as an edge in the graph, it would be classified as a forward edge in this particular DFS run, if there was a particular edge, but there is no edge. So, now since it is over, what happens? C is over and the finishing time is 8. Now, let us call DFS with A. Now, when you call with A, it becomes 9, that is the discovery time, and from A you can go to B, but we discovered C already, it is already processed. So, it is a cross edge, okay, because we do not need it. Now we discover the vertex B. So, we discover it. So, the name changes to the discovery time becomes 10 and we have discovered it. Now, from B to D is a cross edge, because now, so we move back to C, okay, and now you move back and you have to put B. Okay. Now, what happened after that? A is done as well. So, you have A. So, and the finishing time that you add. Okay. So, what we have done is we have the result, return the linked list of vertices. So, this is the list of vertices that you have. So, what have we actually done? We have put 2 times associated with each edge, and we are also marking cross edges, we are marking tree edges. So, we are using the depth first. So, from C we are going to D to F, that is the depth, and after you finish F, okay, you are going back to D and you are going back to C and you are finding E. Now, from E you can only go to edges that have already been discovered, D and F. So, they become cross edges. Okay. Now, after you go back to C, you have nothing else to do. So, there is no other edges from there. So, you stop. Now, you start with A. Now, when you start with A, you can go to B and C, but C is already discovered. So, it becomes a cross edge, and then you go to B. Now, B to D is a cross edge. So, B is over. So, the times are fixed approximately and you have a time as 30. So, this is the way topological sort is done using a depth first search. Okay, depth first search means you follow edges as you go along. So, C to D to F, C to E, after that you do not have anything because there are no edges, A to B. So, there are C D F is 1, C E is 1 and A B is 1, and the order in which it will come is you first finish F, then you finish D, then you finish E. Once you finish D and E, you finish C. Once you finish C, nothing else finishes there. You start from A, you can go to B. So, you do B first. Once B is over, you can finish A. So, that is the topological sort. You have done a topological sort as an application of a DFS. The linked list is sorted in decreasing order of finishing times. So, A has got the maximum finishing time 12, B has got the next 11, C has got 8, E has got 7, D has got 5 and F has got 4. Okay. And you can also try this with starting with some other node. If you redraw the graph so that all vertices are in a line ordered by the valid topological sort, then all edges point from left to right. Now, let us look at the time complexity of the topological sorting of a graph. So, the running type of the topological sort will be the order of n plus m, where n is the number of nodes or vertices and m is the number of edges. Okay. Now, why? Because depth first search takes 0 n plus m time in the worst case, and inserting into the front of the list takes only about of the order. So, actually what you are doing is a depth first search, and in addition what you are doing is you are inserting into a linked list. So, that takes constant time. So, the order of the topological sort of n plus m is approximately the order, it is the same, almost the same as the order of the depth first search of the same graph. Okay. The complexity, we never visited a vertex more than one time. For each vertex we had to examine all outgoing edges, out degree of the vertex equal to m. So, summing up all vertices, not per vertex, you get approximately the summation of that is m. So, our running time is the visit of the n vertices n plus the examining all outgoing vertices m. So, of the order of n plus n. Now, why do you say that our topological sort produces a topological sort of a graph DAG G? How do you know it is correct? So, topological sort G algorithm does a DFS on the DAG G and it lists the nodes of G in order of decreasing finish times. Okay. Now, we must show that this list satisfies the topological sort property, namely that for every edge uv of G, u appears before v in the list. That is what we want. Claim for every edge uv of G, f of v, the finishing time of v is less than the finishing of time of u in the DFS. So, for every edge u of v, we assume that the finishing time of v, remember what is the discovery time and finishing time which we discussed before, is less than the finishing time of u in this DFS. DFS classifies uv, that is as a tree edge, a forward edge or a cross edge. It cannot be a back edge, though we defined a back edge, because as per the definition G is a DAG and does not have any cycles. Remember, tree edge is the traversal by the depth first search, that is the forward edge where u is before v, and backward edge when v is before u. So, if v is a tree or a forward edge, v is a descendant of v. Okay. So, the finishing time of v will be less than the finishing time of u. If it is a cross edge, okay, if it is a cross edge, as uv is a cross edge by definition, neither u is a descendant of v or v is an descendant of u, either way. Therefore, d of u is less than f of u, less than d of v less than b f of v, or d of v is less than f of v is less than d of u is less than phi of v. Since uv is an edge, we surely discovered before u's exploration completes. Therefore, if it is an edge, okay, v will be surely discovered before the exploration of u completes. So, this is the claim that the f of v is less than f of u. Okay. So, that is what. So, by the claim topological sort lists the nodes of G from highest to lowest finishing times. By the claim for every edge uv of G, f of v is less than f of u. So, first you have the v uv edge, v comes first and u comes next. So, u will be before v in the algorithm's list. That is the proof of the theorem. Now, here we discussed the concept of topological ordering, but we discussed it as a application of depth first search. So, we did not keep any neighbors or anything. What we did is we classified the edges into a tree edge, a forward edge, tree edge and forward edge, and then cross edge. We do not use backward edge, because as the definition DAG, it is a DAG, that is graph is a DAG and it cannot have a backward edge. So, these are the three edges we consider. So, what we do is start with a node and carry on going till you reach a point where you can go no further, and at that point that is the first finishing node. So, that is a descendant of the other node. So, its finishing time will be less than the finishing time of its ancestors. So, we explained the concept of topological sorting and we discussed in a very in less detail, but we just briefly looked at the proof of correctness of the algorithm. So, thank you.